Thank you all for coming today, and thanks to John and to Oxford for the invitation to be here. So I'm very excited to tell you about an area of research that's very active in the mathematical community, but also in the world more generally. And if you read any of the blurbs advertising this talk, I posed the question of what the three items that you see on this screen could possibly have in common. So we've got grocery shopping on the left, we've got maypole dancing on the right, and in the middle we have something where the resolution isn't as good as I thought it was when I had this on my laptop, but that's the quadratic formula, which describes parabolic graphs in motion. And the answer, or at least an answer to the question of what these three things have in common, is braids. And what I want to convince you about today is not only is that a valid claim, but also that once you understand a different viewpoint than perhaps you might have at present about braids, actually braids are just about everywhere. And so that's the journey that we're going to take today. And before I get started, I really need to give a particular thanks to Benson Farb, who's a professor at the University of Chicago. So he's a former collaborator of mine, and he has similar research interests, and he provided many of the animations and I will say a lot of the inspiration for this talk. Okay. So braids are something that we see commonly in the world. Sometimes people use the word plait. So for mathematicians, that means something slightly different than what I'm going to describe. But here we have some challah bread, so braided bread. In the middle there, we have the great Venus Williams. Hair is something that we commonly braid. The Book of Kells, something else that illustrates the intricacy of braiding patterns. So we have braid in art as well, many other places. I'm sure you can think of examples. But let's start with hair, okay? So I'm not very good at braiding hair. You can ask my daughters. I've had short hair for a long time, so I never really learned. But the basic idea is simple, right? So you take 3 strands, and you go one over the other, left side, right side, left side, right side. Okay? So how do we model that mathematically? That's the question. So here is an illustration of the standard hair braid. So here are sort of 7 sequences where, in this case, if you're able to see the colors, that sort of helps you see the stages, but if you can't see them, it's just the same pattern that we saw before in the photograph. So we have 3 strands, left one goes over the middle and becomes the middle one, and the right strand then goes over the middle one, and then that becomes the middle one. And then we just keep going left over middle, right over middle, left over middle, right over middle. And you can see here that we have a sort of abstract representation of the standard hair braid drawn as sort of 3 arcs, and they have these little, I don't know if you can see the laser pointer, but they have these little overlapping periods where these little gaps are meant to indicate that in this example, the strand that starts out on the left is coming down and going over the strand in the middle, and that's what that little gap is meant to represent. Okay? Any questions about that? Okay. Okay. So sometimes we do that, partly because, so instead of having our strands going top to bottom, it's easier to draw them going horizontally. And that's partly because in this talk, I have more horizontal width than I do vertical width. it also makes it easier for mathematicians to incorporate these into our research papers and get them published. So depending on the context, we will go back and forth. So sometimes we go like the hair braid, top to bottom, but sometimes it'll be more convenient to do the sideways version. And they're both equivalent. Okay, so how does a mathematician understand this object? Let's start with that. So this is something that we call a geometric braid, and I want to tell you a little bit about some of its properties. So for starters, we don't consider them as completely rigid objects, okay? So just like your hair can kind of slide around, so if you have your hair braided, it might not, stay perfectly neat, but roughly the same over-under patterns are going to stay put, okay? But also your hair is not going to come detached from your scalp, right? Well, at least we hope not. Or maybe that's what you want, you do you, right? But like this is recorded mathematically by the fact that we fix the endpoints. Okay, so these sort of black dots here are meant to represent the fact that I'm not allowed to move the endpoints of my braid. But we have something called isotopy, which means that I'm allowed to kind of wiggle and stretch everything else in the middle, as long as I don't sort of violate the obvious rule of hair braiding, which is you can't let one strand pass through another, because that just doesn't happen without breaking your hair, okay? So for example, this strand that starts out on the top left here and crosses over the other two, it does the same thing down here in the second picture, but it does it sort of first, and then this crossing between the two strands that start out in the second and third position is now happening over here. Okay, so I can do that without moving the endpoints, and I can do that without having the strands pass through each other. I just need to let them wiggle in the middle. So there is a formal mathematical definition, of course, of isotopy, which can be framed in terms of continuous embeddings, if you know what that means. But really, it's just wiggling while holding the endpoints fixed. And if you think about it, it makes sense that we would have that constraint, because if I was allowed to move the endpoints, then this is just the most boring theory ever, right? Because everything would just come undone, and we wouldn't have anything to talk about today, okay? So here's an example of braid isotopy, and here's another example of braid isotopy. So here I have a 4 braid, so 4 strands, and I've got a crossing between the top 2 and a crossing between the bottom 2, and here, sort of as I go left to right, the bottom one happens first, but I can just kind of slide them past each other. So here, the top one's happening first. And we say that those are the same braid, okay? Okay, so that's what a mathematician means when they're talking about a braid. And now I want to tell you one reason why we're interested in braids. And the reason is that they turn out to be a useful object if you're doing algebra. So we're going to go back to the algebra that we all learned in school. So if we're just doing algebra, whatever year you might have encountered this, I'm not sure how it works in England. I clearly didn't grow up here, you can tell. So if you're thinking about your favorite set of numbers, I'd like to think about what are called the rational numbers. That's denoted by Q. So these are numbers that can be represented as fractions. If you want, you can also think about the real numbers, where you allow things like the square root of 2 or pi, things like that. So let's suppose I give you the equation 5 times n equals 15. Okay, now you're going to be on YouTube. What's n?
3.
Very brave person. Thank you. Okay, so we all know the answer is 3, or we'll pretend we all did. But let's think about algebraically how we get there, okay? So like, if we didn't know that, then my strategy might be, well, I want to solve this equation for n, okay? And to do that, I need to get rid of the 5. So you probably say, why don't you just divide by 5? You know, what's up with the 1/5? That looks maybe unnecessarily complicated, but I want to do this by being efficient with operations. Division is a different operation than multiplication. So I'm going to try to do all of this with multiplication. So I've got 1/5 times 5 times n, right? And what I'm doing here is I'm taking the left side of the equation and the right side of the equation, I'm multiplying each of them by 1/5, okay? So you're thinking, okay, we all know this, but let's keep going. So the next thing that I need to do is, instead of multiplying 5 by n, I need to pair 5 with 1/5. And the reason for that, I think we all probably know, is because that'll give us 1. And 1 times, and even though we don't know what n is, 1 has the property that 1 times any number is itself. So I can now conclude definitively that n equals 3. So now let's unpack that a little bit. And what are the key properties here? So I'm going to throw some mathematical terms at you, and you can take them or leave them, but we start out with an operation. So I said I wanted to use just multiplication, not division. Multiplication is a binary operation on Q, okay, on the set of rational numbers. So, and again, you can think about real numbers if you want. So what that means, binary just means you put two things together and get something else that's in the same set. So if you give me two fractions, I can multiply them together and I get some other fraction. That's all that that means, okay? So I've got this operation. And so what's the next property I need? So as long as the thing I'm multiplying by here, so 5 is the thing we kind of want to get rid of because we're trying to solve for n. So as long as 5 isn't 0, which it's not, right? I can find an inverse in the world of fractions, right? And if the number that I was multiplying by here were 0, then this equation would never be true. So that's kind of so we sort of throw out 0. But any other rational number has an inverse under multiplication. So that's why we chose 1/5. Multiplication also has the property of associativity, right? So if I have 3 numbers and I tell you multiply them together, probably what you're going to do is like visually scan and pick the easiest pair next to each other and do that first, and then do the last one. At least that's what I do when I multiply 3 numbers. And that just means I'm moving the brackets, okay? So I can do that. That's called associativity, and that allows me to pair 5 with its inverse, and then, oops, right? Inverses again, the whole reason I chose 1/5 was because it was going to pair with 5 to get this special number that has this property. It's called the identity element, okay? So that's just the name for something that has the property that I talked about before, that if you multiply it by anything, you get the thing you started with, okay? So 1 times n is always n, no matter what, okay? That's the identity element for multiplication, okay? Okay, so that's doing algebra with numbers. And what I want to explain to you now is how to do algebra with braids, okay? So the first thing we're going to need is one of these binary operations, right? So I'm going to need to find a way to take 2 braids and combine them to get a 3rd braid in a way that has hopefully some of these nice properties. Okay, so here we go, hopefully. Okay, so there's braid number 1. So these are 3-stranded braids. Braid number 2. And the operation is take the first braid, stick it on top, take the second braid, stick it on the bottom, and then scale it down. Okay? So that's called concatenation. So here's just the end of that. Break that down. So, so here we're doing obviously the vertical version, but you can do a left to right version as well. So here's the first braid, and there it is, sort of cutting off there around where the height of the equal sign. And there's a second braid below, and then just to keep things nice, we rescale. And this is a binary operation. Now, I'm sort of cheating here in the sense that I just want to insist that all my braids have the same number of strands. But I'll say, okay, we're working with 3-stranded braids, say, or 4-stranded braids, or 100-stranded braids, whatever. And as long as I fix the number of strands, I can do this, okay? And this is clearly associative because if I take, so if you think about the left to right version, I take braid 1, braid 2, and then stick on braid 3. And that's the same as if I stuck braid 2 and 3 together and then put 1 in front, okay? So we have a binary operation that's associative. Now we just need an identity element and inverses, and we can do algebra, right? We can solve basic equations. So what's the identity going to be? I should have just paused here and let you guess. So, I mean, multiplication by 1 does nothing. So what kind of braid does nothing, right? This is a non-braided braid, right? This is like you just combed your hair instead of braiding it, right? So that is the identity element. And let's just see how that works. I take some other braid, whatever it is, I concatenate, and I fix those endpoints, and there's just nothing going on here. So when I shrink it down, oops, right, I just get the same braid that I started with. And that would happen if I did put the identity braid on the other side. So for any number of strands, if you just take that many strands and run that many parallel lines, that's your identity element for this operation. So before we get to inverses, I want to talk a little bit about simpler braids. Okay, so the braids I've been showing you aren't super complicated so far, but the most basic thing you can do when you're braiding hair is take one strand and pull it over the next strand, the one that's right next to it. So if I have n strands, so here I've got, the first strand and the nth strand and then something in the middle. So if I've got the kth strand, so k is some number between 1 and n, and I let the strand to its right come over top of it, so this is the simplest kind of braid that you can do. One strand over the other, over the one next to it. And we call this sigma k. I'm not sure why it's sigma. It just is in most of the braid literature. So sigma k, one strand over its neighbor, is the simplest kind of braid that you can have. Okay? And okay, so let's look at the sideways version. So here's sigma k. So that's k plus 1 coming down over the kth strand, as I've labeled them here. What's the difference between these two pictures? Right, so instead of this one coming down and over, it's coming down and under, right? That's going to be our inverse element, okay? So why is that going to be our inverse element? Well, let's stick them together. And remember, we're allowed to do isotopy, but these are not endpoints anymore. Now they're in the middle once I've stuck them together. So they're allowed to move now. It's only the endpoints on the left and on the right that I can't move. And so I can do my isotopy and just kind of pull them tight. So now I have an inverse, at least for sigma k. And yeah, there's our identity element over there. And one thing we can notice right away is that this dashed line shows us that the inverse of sigma k is nothing other than the reflection through a mirror, right? And actually, if you think about it, that's going to give us inverses in general. Okay, so it turns out that we can write any braid as a sequence of these sigmas and their inverses, because if I want to cross the bottom strand over the top strand, I have to cross the neighbors in between, right? So each braid, no matter how complicated, can be broken down into these little chunks of sigmas and sigma inverses. And then we can just, if we want to undo them all, we can just undo them one at a time by holding up a mirror, okay? So we've got inverses as well. So one reason that we like braid groups is it's this geometric object, or topological object is another word we use. But you can encode braids as symbols, and you can do algebra with it. So you can write down equations, you can solve equations, and you can embed topological pictures in a very computational setting. So this is one reason that mathematicians are very interested in this structure. But I promised to tell you about other things, right? Groceries and maypole dancing and the quadratic formula. So, okay, so I want to give you an example of braids in the real world, right? Because that's all nice abstract stuff, but where do braids show up in real life? Okay, you probably weren't, was anybody expecting a football? Probably not, okay? So I'm going to take a football and I'm going to kick it up, and it's going to trace out a parabola. And I can ask the question, at what times t is the ball at some particular height? Right? That's a reasonable question to ask. Maybe we don't care so much about footballs. Maybe we care about when they hit the ground again, but this is a question we can ask about any sort of projectile, right? And so let's look at the solutions that we can find here. Now, if h denotes the height of our football at time t, right? So if I start when the football is on the ground, we know there's two solutions. There's when I kick it and when it comes back down, right? And if I say, well, what about when it's, say, I don't know, 1 meter high? Maybe there's still 2 points where it goes up to 1 meter, keeps going a little bit, passes the same height on the way down. Same for, say, 2 meters. But we get to the top of the arc, and we get this sort of weird singularity. There's just one solution there. It's at that point just for a minute, then it drops back down. And if we go any higher than that, there's no solutions, right? There are no times where the football hits that height. It just doesn't happen, okay? Now, so anybody who's had a little bit of physics will know that this is the equation that describes this parabola. So we have h is given by the initial upward speed times the time that's gone by. And we have another term which involves the acceleration due to gravity, which it's been a long time since I took physics, but I think it's 9.8 meters per second squared. Is that right? Okay, this will be on YouTube, so we can't wait to see the comments if that's wrong. But anyway, so in order to answer the question, we need to solve what's called a quadratic equation. And we also call this a degree 2 equation because the highest power of the variable t that we see is 2. Okay? So another way to phrase that is we need to find the roots of this particular polynomial, this quadratic degree 2 polynomial. Okay? So luckily, there's the quadratic formula. Okay? So how many of you have seen this at some point in your life? That if you want to solve ax squared plus bx plus c equals 0, x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. I feel like, yeah? Yeah. Great. I always think that, you know, when I'm retired and I'm in a home or something, I can't remember my own name, I'm just going to be wandering around just reciting that because I feel like that's something that's always going to stay with me. Okay, so, all right, so what's really going on here with this football? So in some sense, the most important part of this formula is the part that's under the square root sign. So we often call this the discriminant, this b squared minus 4ac. And why is that important? Well, let's go back to our picture here. So for the particular equation we need to solve, it turns out this is what the discriminant is. But we're not really interested in physics here, so I'm just mentioning that in case you were curious. But if you were to calculate that, then at height 0, you're going to see that the discriminant is positive. Still positive. Still positive. Not positive, but not negative either. So this is the singularity when the discriminant is 0. And the key difference when I get to the point where there aren't any solution is that the discriminant is negative, right? So this is what's going on algebraically when I draw these pictures and I see how many solutions there are for the football being at a certain height at particular times. Okay? And the reason for this is because taking square roots of negative numbers doesn't make sense in the context of a football being kicked, right? So we can't find real solutions to this equation in those cases. Okay. But we're mathematicians, right? So we don't give up. We say, well, okay, maybe there's something we can say. And so let's solve a simple quadratic equation. X squared equals 1. So you can think of this in the other form as x squared minus 1 equals 0. Okay, so time to ask the audience again. What are the solutions? What are all the values of x that would make this equation true? Plus or minus 1. Great. So there's two solutions. X is 1 or x is minus 1. And we can think of that as taking the square root of this number over here and making sure that we also include the negative of that number, right? Okay, so that's something that we can do. So, but what happens if I wanted to solve the equation x squared plus 1 equals 0? So then I have x squared equals minus 1, and then I'm trying to take the square root of a negative number, and we just said we don't know how to do that. Okay, so again, we're mathematicians, so we just make a definition, right? We just define the problem away. We're good at that. We just say, okay, I'm going to make up a number, and I'm going to call it I, just to make the notation a little bit easier. And I want I to have the property that it is the square root of negative 1. In other words, I times I equals negative 1. So because I'm a mathematician, I can just do that without fear and without worrying about whether this makes any sense. So I can take away the question marks in particular. And I can just say, okay, I've solved the equation x equals plus or minus I. Yay, right? And now I can solve all kinds of equations, right? X squared equals minus 25, right? So I can say x equals plus or minus the square root of minus 25, and I can use properties that I know about square roots to kind of split things up. And so I can think about this as the square root of 25, which I know is 5, and the square root of negative 1, which I now know is I, okay? So I've got two solutions to that equation now too. Okay, so we're in business. We can solve quadratic equations now when the discriminant is negative. Okay. So what I want to convince you is that this has geometric meaning. Okay? This isn't just mathematicians making something up and just doing it because they can. There's something geometric going on. Okay? So when in doubt in mathematics, draw a picture. That's the best advice that I can give you. When the algebra isn't giving you the insight, draw a picture and see if that helps. So let's think about what happens when you multiply the number line by negative 1. Okay? But I don't want you to think about numbers. I don't want you to think like, okay, minus 1 times 3 is negative 3. I mean, you can think about that. That, you know, it's not a bad thing to think about. But what I want you to think about is what's going on geometrically. So if I take this whole number line, multiply by negative 1, the only number that's going to be fixed is 0. And what's going to happen to everything else? It's going to flip, right? So geometrically, multiplying by negative 1 is rotating the number line in the plane by 180 degrees, okay? So geometrically, that's what multiplication by negative 1 is. It's a rotation. Okay. And if I do it again, oh, I get back to where I started, right? And that's because negative 1 times negative 1 is 1, right? As we saw in the first equation that we solved. Okay. So how can we think about the number that we just defined, I, the square root of negative 1? So negative 1 times negative 1 is 1, because negative 1 is squared is 1, right? So if I want to multiply the number line by the square root of negative 1, then by analogy, geometrically, I should be doing something that when I do it twice has the same effect as multiplying by the number under the square root. So if multiplying by the number under the square root is rotating by 180 degrees, and I want to get there in 2 steps, then what I'm going to do is rotate by 90 degrees. Okay, so if I want to multiply the number line by the square root of negative 1, then geometrically, I want to think of that as rotation by 90 degrees in the plane. And if I do it again, then I get back multiplication by negative 1. And you know, we can keep going, right? So I can do it again, and I can do it again, and I get back the original number line. Okay? So this is how you should be thinking about the square root of negative 1. Not with some formula that somebody hands you and said, okay, great, you can solve quadratic equations, although that's, you know, useful, but it's a geometric thing. It's rotation by 90 degrees instead of by the full 180 degrees. And so this is something that we call the complex plane. So we take these 2 axes that appear when we do this, and we keep the horizontal axis as the number line that we're used to, but we sort of have a copy of it that's indexed by multiples of I now, instead of just multiples of 1. And the complex plane has a really rich structure, okay? So how many of you have seen complex numbers before? Great, okay. How many of you knew it was rotation, that I was rotation by 90 degrees? That's so great. Oh, good, so people are drawing pictures for you. So here's moving around in the complex plane, like, so it's not just the axes, right? So I can start to like use these as coordinates. And I can go back to I can go back to the quadratic formula now. And now that we know that there's meaning to this, and now that we know that we can take square roots of negative numbers, the quadratic formula is telling us that if we work over the complex plane, except for these singularities where maybe you get a single solution, but that's sort of a drop in the bucket, right? So there's, you know, in the height example, there's one point out of uncountably infinitely many that has just a single solution. So in general, a quadratic equation has two solutions. Now, the quadratic formula is something that we know, that we get taught in school. There's something called the fundamental theorem of algebra that maybe you learn if you do an undergraduate degree in mathematics, that tells us that in general, if I take a degree n polynomial, there will be n solutions in the complex plane. Okay? So there will be these singularities where you get fewer solutions. And what that means is actually some of the solutions are going to repeat themselves. So like plus or minus 0, plus 0, and minus 0 are the same thing. Okay? So back to quadratic equations. I'm going to make one simplification before I can explain to you how this relates to braids. So this version is the one that we learn, and we have the formula that we can all recite, but it's unnecessarily complicated, right? So I don't really need to consider quadratic equations with an arbitrary coefficient a here, right? I can just, assuming a isn't 0, in which case it's not a quadratic equation, it's linear, we can just divide through by a and simplify this. So I only get these two parameters instead. And this is something called a monic polynomial. It means that instead of multiplying x squared by an arbitrary number a, I'm only going to have 1 there. And I don't write that down, because 1 times x squared is x squared. And what I want to introduce here is, sorry, I just saw the movie Everything Everywhere All at Once or whatever, so that was what was in my mind when I made this slide. Poly n is the space of roots of all monic polynomials of degree n, except for these singular ones that we don't really need to worry about. If we have repeated roots and we find one root, then we're already winning. So there are ways to deal with those. So I'm not really cheating at all by ignoring those. And the idea is that if I give you 3 distinct roots, then because I'm insisting on monic polynomials, I can write down a specific polynomial that has those 3 roots. Okay? And I can do this for any number. I'm just doing it for 3 because that's what fit on the slide. And again, I'm just realizing, okay, yes, this is going to go on YouTube. I really hope that's correct. And the point is that we get a uniquely determined monic polynomial. So, and it goes the other way, because the fundamental theorem of algebra tells us, right, that unless I'm in one of those singular situations, then I'm going to get 3 distinct roots. Okay? So in other words, I can understand the space of all polynomials all at once by just considering a set of numbers, right? So if I want to consider polynomials of degree n, I can think of that precisely as a set of n numbers, okay? So this gives us a really different take on understanding polynomials. So let's just look at some examples. So So what I want you to think about is that I think I won't have trouble convincing you that this is a point in poly 2, right? Poly 2 is the space of monic degree 2 polynomials. So x squared minus 2 is a point in this space. But I can also think of a point in this space as a pair of points in the complex plane. The pair together is 1 point. Okay? I named these two, and I've named this monic polynomial. So if I change that to x squared plus 1, I get a different point in poly 2. I get a different pair of points in the complex plane. Okay, so x squared minus 4, we'll just go through some examples, right? So the roots of that are 2 and minus 2. If I change that to x squared plus 4, then I'm going to get 2i and minus 2i. And then I can sort of do some more interesting things. They're not always nice and symmetric like this. So this monic polynomial has roots minus 2 and 3. And this one has roots 2 plus I and 2 minus I. We can also just start using complex numbers themselves as coefficients in our polynomials, because why not? Okay? We've decided they're meaningful, so let's do it. So what I want you to picture now is that we live in the space poly 4, right? So we're in degree 4 polynomials. So I'm trying to do something a little bit more complicated than quadratics here. So the quartic polynomial, the degree 4 polynomial x to the 4th minus 10x squared plus 9, has these 4 distinct roots. Okay? And so there are colors there. If you can see them, it might help you follow them around, but we don't need them. They're not, there's nothing important about the colors there. So what does it look like to move around in the space of polynomials? So, I mean, I could do it here, but I get a much better visual intuition doing it in the complex plane. So a point in poly 4 is the set of these 4 points. Okay? So 4 points in the complex plane gives me 1 point in poly 4. So if I'm moving around, all I'm doing is letting these points wander around, and the only thing they're not allowed to do is crash into each other, right? Because that would take me into one of those singularity situations that I don't want to consider. It's not in my space. So moving around in poly 4 is just taking 4 points and letting them wander around without crashing. So there's 3 different ways we can understand the space of, they're also called square-free polynomials, no repeating roots, none of these singularities. I can think of it as the space of n distinct complex numbers. And in some sense, I can even forget about the complex numbers and just think about these as n distinct points in the plane, right? And just forget about the fact that I've given it this sort of structure. Okay? So when we watch these 4 points moving around, and notice that they didn't just land anywhere. As a set, they landed where they started, right? So they started at a point in poly 4, and they moved all around poly 4, and they moved all around, but they came back to the same original point. We call that a loop, right? A loop is when you start somewhere, like, and you go out onto the street and you wander around and you walk around the block and, I don't know, take a little detour somewhere, but eventually come back to where you started, right? So this is a mathematical object that we understand how to study. So there's a whole field called algebraic topology that studies loops in spaces. There's a whole theory there. And that's all that a braid is. So braids are just loops in a configuration space. Now here, I haven't drawn the whole plane because I don't really need to, but I've got 3 points. I'm just going to focus on a disk, right? Just a little neighborhood of those points. You can imagine this is the whole complex plane extending out, but you'll see in a minute why I just want to focus on a little neighborhood here. And think about watching a movie of those points moving around in this space. So you don't have to think about it because I'm showing it to you, right? And here, as we move down each level, right, we've got what the braid is doing is it's recording the motion of those 3 points on the plane. And it's not just recording sort of where they end up, it's recording sort of this one moved around in front of this one, and this one moved behind this one. So a braid is just a loop in one of these spaces, the space of configurations of 3 points in the plane, which we can also think about as the complex plane. Okay. So that gives us a natural sort of dictionary between our sort of geometric intuition of intertwining strands and motion on a surface, right? Keeping track of points on a surface. So any braid that I have, I can kind of think about that movie we just saw of moving the disk down and see what happens to the points of intersection of that disk with the braid. And at each such slice, I'm going to get a picture like the one on the left here. Okay? So braids are just recording motion in a plane. Or if I want to do something finite in a disk. Right? Oh, I put labels on them. Sorry, forgot that. Okay. So let's go back to braid building blocks. Okay, so let's think about what this means in that context. So on the left here, I have the geometric braid that we called sigma k. And if you think about the movie version of that, right? So what happens as you watch the film of these points as you move down? Well, what's happening is k plus 1 is kind of moving around in front, and k is moving around behind. Now you have to imagine that you're sort of standing and looking down on the braid while this happens. And so the building block of every braid is just 2 points next to each other in the plane trading places. Okay? And this always makes me think of when I was a kid, in gym class in the US, they made us do square dancing. They don't probably make you do square dancing, like English country dancing or something like that. I mean, my kids go to school in Scotland. They had to do, they called it social dancing, like Cayley dances. Does anybody know what a do-si-do is? Yep. Okay. So the building blocks of braids are just do-si-dos. That's all it is. It's 2 people, or in this case, 2 points, changing places. And the reason I put maypole dancing in the blurb for this talk is because it perfectly encapsulates both perspectives on braids, right? So we've got the configuration space of bodies in motion. So in this case, it's the dancers on the lawn, right? They're moving into each other and they don't want to crash into each other, right? That's really, really bad when dancers crash into each other, okay? But we've also got the geometric braiding around the pole, right? The strands of the ribbons are encoding the motion of the dancers in a very concrete way. So maypole dancing is exactly telling us about this different perspective on braids. but also on polynomials, okay? So imagine each dancer is a root of a polynomial, right? Okay. I'm sure that's what they're thinking about. So, but once you start realizing it's about motion on a surface, it's everywhere, okay? Configuration spaces, things moving around and you don't want them to bump into each other, that's everywhere in the world. Okay, so you don't have to be a maypole dancer, you could just be at a wedding or something, right? So we hope the groom isn't crashing into his mother there. But like more importantly, I mean, I flew down this morning and, you know, that's a pretty important, you know, 30,000 feet in the air, that's a pretty important configuration space as far as I'm concerned, right? Because, you know, that's what air traffic control does. Now, what about over here? So, does anybody know what this picture over here is? Somebody said it. Yes. So, this is an Ocado warehouse. And guess what? Its floor is just a configuration space. And they don't want their robots to crash into each other. And so they definitely have a vested interest in understanding the space in which their robots can move around. So this is a really important example of configuration space. I think you might have seen in the news, wasn't that long ago, maybe 3 or 4 years ago, there was a big fire in Ocado warehouse because 2 robots did crash into each other. So they weren't respecting the rules of the configuration space. You know, and this is our new way of getting groceries, right? Like this is, so Ocado is, you know, we don't, you know, I don't know about you all, but, you know, my family made the transition from this to this during the pandemic. And this is something I think that's going to be with us for quite some time. And it's not just groceries, right? So a lot of this kind of warehouse type economy is moving in this direction. So braids are everywhere in maths. I've sort of told you about why we're interested, because we can do algebra with them. I've told you about sort of some of the geometry and topology. They also come up in analysis in various ways. If you're interested in fractals, there's really interesting problems to do with solutions to polynomials, and you get like Julia sets and twisted rabbits and things like that. So these kinds of pictures here. Braids also appear in physics, and I just want to end by mentioning 2 examples. So solar flares, braid. So we had a conference several years ago in Edinburgh that was kind of bringing together people who were interested in braids from different perspectives. And we had sort of astrophysicists talking about problems about braids that they wanted to understand because they see this kind of phenomena. Over here, we have a very different sort of thing. Does anybody know what this is a picture of, these 2 items on the right? So these are something called anyons. So this is sort of a quantum field kind of thing. So these are particles, and they form rings. And so a long time ago, I did some work on configuration spaces where instead of points moving around in a plane, you had rings moving around in 3 space. So, you know, they can move around like points, or one can go through another one and then back over it. So you can have all kinds of configuration spaces. It doesn't just have to be points. Any sort of body that you're interested in. And then I started getting invitations to speak on this, and I thought it was like topologists being interested or algebraists being interested. It turned out it was a mathematical physics, like I'd get to the university to give a talk on these configuration spaces. It was always a mathematical physicist who it turned out had invited me, and you know, they wanted to know about these motions of rings because they were interested in the theory of anyons. Okay, so braids really are ubiquitous. If you go to Dublin, I had to do this, obviously. There's me with, if you ever go to Dublin, go to the Botanic Gardens, find the braid. That's your assignment. It's a big place. Good luck. And I just want to end by showing you some of the other people who are interested in braids. These are people I've collaborated with on this topic over the years. You'll see Benson, who I mentioned at the beginning. Here in the middle is Joan Berman, who is my PhD advisor. And she's going to turn 97 next month. And we're collaborating on a project on braids. She's amazing. All these people are amazing. So I want to say thank you to them and thank you to you for being here today.